Hello friends, welcome to the next session. Here we are going to solve big problems where we are going to convert regular expression to minimize deterministic finite automata. So let's get started. Now to convert any given regular expression to non-deterministic finite automata, there are a set of steps to be followed. Before that, let us understand how the conversion is going to go ahead. So for converting a regular expression to a minimized DFA, the first step is to take the regular expression. So a question will be given to you in the theoretical form and you will be required to form a regular expression for it. This topic we have already covered previously. So you should know how to write a regular expression. After that, this regular expression we are going to convert it to non-deterministic finite automata. This also we have covered it previously. Later on, this NFA will be converted to a deterministic finite automata by us, and finally this DFA is going to be converted to a minimized DFA by us, of course by using certain steps. So a problem over here is going to come for 10 marks over here. So in case if you don't know what is a regular expression, or if you are unable to write the regular expression for the problem stated, you cannot solve the further part of the problem and you have to skip that problem. So understanding what is regular expression is important, and getting it converted to NFA is equally important. If you are able to do those two steps, then you will be able to convert and solve the entire problem. So let's get started with the question now. So the problem which is given to us is construct a minimized DFA to recognize set of all strings ending in ABB over the alphabet AB. So the step number 1 over here that we are supposed to write is going to be the regular expression. Now what will be the regular expression for set of all strings ending in ABB? We already know that it has to end in ABB, so we write ABB over here. Since it has to end in ABB, anything after ABB is not acceptable, whereas it can have anything before ABB, and that anything is nothing but any combination of A's and B's, denoted by A plus B the whole star. So I have my A plus B the whole star over here, and the diagram for this we have to draw it in the step number 2. So let's go ahead with the diagram in step 2. So my step 2 says drawing the NFA for my regular expression A plus B whole star ABB. So let's draw it. So I have to draw initially NFA for A. So this is my NFA for A. I have to draw NFA for B. That is my NFA for B. Further draw NFA for A plus B. So that is my A plus B connected by epsilon. Epsilon. Here to epsilon. Epsilon. So NFA for A plus B is ready. Convert it to A plus B whole star. So append a start state and one state at the end. There will be a reverse transition from here to here on epsilon, and a forward transition from here to here on epsilon. Connect this via epsilon and this to via epsilon. Call this as my start state. So that completes my A plus B whole star, but it has to end in ABB, so append those states. So going ahead, we have A over here, we have B over here, and lastly we have another B over here. Label those states. So we have 0, 1, 2, 3, 4, 5, 6, 7, A over here, 8, 9 and 10. So total of possible 10 states. Now moving on to the next step. So step number 1, regular expression. Step number 2, converting that RE to NFA. What is the third step? Yes, NFA to DFA. So coming to step 3. So my step 3 is NFA to my DFA conversion. Now for converting NFA to DFA, we are going to have a table, and that table is going to consist of epsilon closure of states. That is the reason we studied that definition before. So now the table is going to consist of X, which are nothing but my states, followed by Y, which will be equal to the epsilon closure of X, followed by my del Y on A, that is Y on receiving the input symbol A, and Y on receiving input symbol B. To start with, I'm going to have 0 as the input. Therefore, why are we starting with 0? The reason is, if you observe the diagram, our start state is 0, and for every conversion we are always going to start from 0. So we write, in place of X we have a 0 right now. So I have my 0 over here, and now it is the time to calculate epsilon closure of 0. Coming back to the diagram, what is the epsilon closure of 0? Let us draw it over here and then paste it over there. So epsilon closure of 0 is nothing but it is going to include 0, 1, 2, 4 and 7. So that is the epsilon closure of 0. Let's write it in the diagram. So we have to be written in the table 0, 1, 2, 4 and 7. Now going ahead, what we are going to do next is, what is Y on receiving A? Now if you look at Y, now Y is now consisting of 0, 1, 2, 4 and 7. We have to check each one of them on receiving A. That is, if we go back to the diagram now, what is 0 on receiving A? I don't think 0 on receiving A is going anywhere, so let's skip that. What is 1 on receiving A? Still not going anywhere. 2 on A, yes, I can see that it is going to 3. Then 4 on A is going nowhere. 7 on A is going to 8. So that accounts for 3, 8. That is nothing but Y on receiving A. So now we are going to include that in the table. So I say Y on A is going to be 3, 8. Similarly, we are going to fill what is Y on receiving B. So going back to my diagram, I have 0 on B, doesn't get anywhere, 1 on B, nowhere, 2 on B, nowhere, whereas 4 on B, yes, I see that 4 on B is going to 5, and 7 on B is also not going anywhere. So epsilon closure of Y on B is going to consist of a single state, 5. So let's write it. Moving to the table, I write over here 5. Now having completed this, the question is what to write or what to conclude now. Now whatever thing you achieved over here, del Y on A and del Y on B will be forming the new rows for the table. So I say I'm going to write over here 3, 8. That is going to be my one row. I'm going to write over here 5. That is going to be my next row. Now the epsilon closure of 3, 8. We already saw what is epsilon closure of 3, 8 in the definitions example. So I'm going to directly write over here. Epsilon closure of 3, 8 is epsilon closure of 3 union with epsilon closure of 8. And that gave me the answer 1, 2, 3, 4, 6, 7, 8. Now what is Y on receiving A? So we have to do that. So I say let us write the set 1, 2, 3, 4, 6, 7, 8 below the diagram. So I have 1, 2, 3, 4, 6, 7, 8. each on receiving A, we have to check what are we getting. So we have 1 on A goes nowhere, 2 on A, yes, it goes to 3, 3 on A nowhere, 4 on A nowhere, 6 on A doesn't go anywhere, 7 on A, yes, it goes to 8, and 8 on A doesn't go anywhere. That is epsilon closure of Y on A. Let's do for Y on B immediately. So we have Y on B, 1 on B nowhere, 2 on B not possible, 3 on B not possible, 4 on B goes to 5, 6 on B not possible, 7 on B not possible, yes, but 8 on B is possible, and that is going to 9. So this is my transition Y on A, and this is my transition Y on B. So let's write it in the table. So I have 3, 8 over here and 5, 9 over here. Now, what to include in the rows? We know that Y on A and Y on B has to be included in the rows. But if you observe closely, 3, 8, that is Y on A, is already included as a part of the rows. So we are not going to re-include it. Whereas 5, 9 was not a part. So write 5, 9 as an additional row in the table. Now go ahead and repeat the procedure. Now we want to find what is epsilon closure of 5. If you observe the diagram closely, epsilon closure of 5 is 5 itself, 6, 7, coming back 1, 2, 4. So let's write the epsilon closure of 5. So epsilon closure of 5 is 1, 2, 4, 5, 6, 7. Fair enough. Going ahead, we have to calculate Y on A and Y on B. For that, we have to move back to the diagram again. So writing 1, 2, 4, 5, 6, 7, that is nothing but epsilon closure of 5. Looking for transitions on A, 1 on A goes nowhere, 2 on A goes to 3, 3 on A we are not looking for, 4 on A nowhere, 5 on A nowhere, 6 on A doesn't go anywhere, but 7 on A goes to 8. So Y on A is 3, 8. Similarly for B, epsilon closure of this, when look for a transition of B, I have 1 on B nowhere, 2 on B nowhere, 4 on B goes to 5, 5 on B nowhere, 6 on B nowhere, 7 on B also nowhere. So I get 3, 8 and 5 to be included in that table. So let's write it. So we have over here 3, 8. We have over here simply 5, and if you observe both of the cells, all of them are already included, so we are not going to add anything in this step. Going ahead, I have to now calculate what is epsilon closure of 5, 9. Epsilon closure of 5, 9 is epsilon closure of 5 union with epsilon closure of 9, and epsilon closure of 5 is already calculated to us in the above cell. So let's only focus on epsilon closure of 9. Going to the diagram, I observe that epsilon closure of 9 is 9 itself because it is nowhere going on 9. So let's write it. So I'm going to have everything what I have above, 1, 2, 4, 5, 6, 7, and my 9 included over here. Now calculating Y on A and Y on B. Coming back to the diagram, writing 1, 2, 4, 5, 6, 7, 9 over here and looking for transitions on A. So if I directly think of transitions on A, I am again getting 3, 8 over here. Whereas if I look for transitions on B, 1 on B not possible, 2 on B not possible, 4 on B yes going to 5, 6 on B not possible, 7 on B not possible, 9 on B is going to 10. So I can see over here that I am getting a new state. So before moving to that, let's add it in the table. So I have over here 3, 8 as input of A, and 5 comma 10 as input of B. 3 comma 8 will be skipped since it was already included, and we have to write 5 comma 10. So let's write over here 5 comma 10. Okay, now calculating epsilon closure of 5 comma 10. If you go to the diagram, you can see that epsilon closure of 10 is nothing but 10, because we know that 10 is the final state and 10 on epsilon is not going to go anywhere. So epsilon closure of 10 is simply 10. So I say epsilon closure of 5 comma 10 is going to be 1, 2, 4, 5, 6, 7 and 10. If you look for y on A and y on B, y on A here is going to give me 3 comma 8. You can of course confirm in the diagram, it has to come 3 comma 8. And on B, I am getting simply a 5 over here. Now if you observe 3 comma 8 and 5, both of them are already covered in the table, so nothing will be added. And there is nothing left as additional rows to be calculated, and here we stop with the transition table. Now it is the time to get this transition table converted to DFA. The main problem is as good as solved. The only thing which is left is certain procedures associated with it, which is going to help us draw a DFA. So what are we going to do now? I'm going to mark the states. So I say I call this 0 as my state A, this as my state B, C, D and E. Of course, since we started with 0, I'm going to mark my state A as my start state, and 5 comma 10 is not going to be marked as the final state. There is again a rule in understanding what to be marked as the final state, and the rule says go back to the diagram. If I observe in the diagram, my final state is the state which is double circled and the number of the state is 10. Remember the number and come back to the transition table. If you observe in the transition table, besides A, B, C, D, E, that is I'm talking of the X column. In the X column, which all are the brace brackets having state 10 included? A does not have, B does not have, C does not have, D does not have, but E has 10 included. Of course, it does not have only 10, but we are not looking for that. We are looking for 10 to be included or not. So we observe that 10 is a subset of 5 comma 10. So since 10 is available over here, that is the reason we are going to mark E as the final state. Had 10 be available in C, D and E both, I'll be marking C, D, E, all of them as the final state. But over here, since 10 was available only in state E, we have marked E as the final state. Now we can solve the diagram further. If you observe my state A, remember state A is called as 0. So I say the target columns over here are now going to be my X column, my Y on A column, my Y on B column. So we are going to basically focus on these 3 columns. So if I observe my A on receiving an input symbol small a, my capital A on receiving an input symbol small a is going to a state 3 comma 8. If you search for 3 comma 8 in X column, we have already given the name to that state as B. So A on receiving an input symbol A goes to B. Similarly, my A, that is 0, on receiving input symbol B goes to 5, and that is nothing but state C. So I write C over here. Then B on receiving input symbol A goes to 3 comma 8, which we again label it as B, and B on receiving input symbol small b goes to 5 comma 9, and 5 comma 9 is nothing but D, so I call this as my state D. Going ahead, I say C on A goes to B and C on small b goes to simplify, and simplify was my C, so I write a C over here. Then D on A goes to B and D on B goes to 5 comma 10, which was my E. Lastly, E on A goes to B and E on small b goes to C. So now whatever we have written in black and red is going to form the new table. So remember, what have we written in the X column? A, B, C, D, E. In the transition of A column, that is B, 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 B. And in the transition of small b's column, that is Y on B, as C, D, C, E, C. So we are going to redraw the table with those values. So let's go ahead. So now I write my del as the transition function and I'm going to draw my DFA. We all know the transition function for DFA is given a state and an input symbol. What is the next state? So I have my Q cross summation over here. I have my A, B, C, D, E marked as the final state over here. Then I have my transitions small a and small b with me, and here I draw my table. Going ahead, I say all of this column had B, 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 B and B, whereas this had C, D, C, E and C. Fine. Now I can see that the table which is in front of me is a deterministic finite automata. That is, from each state on each input symbol there is exactly one transition. However, the question over here doesn't ask us to sketch a DFA. It is asking us to sketch a minimized deterministic finite automata. So now we have to think of the procedure to get this automata converted to a minimized one. So the steps to convert a DFA to minimized DFA are going to be as follows. So I write, for creating the minimized DFA, the rule is going to be as follows, and the rule says states can be merged if the following two conditions are true. So I say states can be merged if rule number one, the rule number one says all the states have the same transitions. So all the states have the same, very important thing, all the states have the same transitions. And most important thing, all the states have the same transition and all should be final or all should be non-final. So I say all are final or all are non-final. Okay, that's the simplest rule for minimization of DFA. States can be merged if all the states have the same transitions and all the states are either final or all the states are either non-final. Now let's get back to our example and apply this rule in that example. Now if you observe the example, I see over here that the minimization rule which was saying that all the states should have the same transitions. So if I observe A on A goes to BC, C on A and B goes to BC, and E on A also goes to BC. Similarly, BD and BE are not getting repeated anywhere. So these are the three states which I have marked with dashes. All of them are giving the same transition, BC, BC and BC respectively. Now the rule says that there is a AND condition. All the states should be final or all the states should be non-final. The marked states over here are A, C and E, and among these states I know that A and C states are non-final whereas E is a final. So I am going to discard state E and think of clubbing only A and C. So I say let us combine this A and C together and call it by a new state name called as X. Now it is the time to draw the minimized DFA, and while drawing the minimized DFA, everywhere we are going to see A and C, we are going to replace it by X in this table. So let's go ahead to minimize DFA. So my step 4, almost the last step, where I am going to draw my minimized DFA, where we know that we have combined states A and C to give a new state called as X. So I have my Q cross summation over here. Then I have, since A was the start state, over here we are going to call X as the start state. Input is A, input is going to be B. After X, the next was B. After that, the next was C. But C and A are combined together, so we need not write it because we have already written X for the same. So skipping C, after this I have D and I have E, which we know is the final state. Now repeat everything. Copy the diagram as it is from the previous diagram, but everywhere you have A and C, we replace it by X. So the first one was X on A goes to B and X on B goes to X. B on A goes to B and B on B is going to go to D. Then C is not there. D on A goes to B and D on B goes to E. Lastly, E on A, B and E on B is going to go to X. Now that is my minimized DFA. After drawing the minimized DFA, the last thing which is left is the transition diagram. Of course, because it holds some marks in the exam. Although my table is also going to be suffice for drawing anything after this. So let us do it. I say my step 5 over here is going to be drawing the transition diagram, or we also simply called as my transition graph. So the states are X, B, D and E. So let's draw it. I have my X, I have my B, I have my D over here and E as the final state, marking this as the start state. We all know the procedure, so let's get started quickly. X on A goes to B, X on B goes to X, B on A goes to B, B on B goes to D, D on A goes to B, D on B goes to E, E on A goes to B. So E on A going over here and E on B goes to X. So that is going to have a big transition from E to X on B. So that completes my transition diagram. Having drawn all this, if you remember the question, it was saying that we have to construct a minimized DFA for set of all strings ending in ABB by using the procedure RE to minimize DFA. So it is the time to solve some examples on it and check whether the procedure was perfect or not. Step 5. Let us consider an example. I say the start state is X. We have to think of the strings ending in ABB. So let us have B, A, B, B as the input. And X on B goes to X. I have ABB over here. X on A goes to B. So I have my BB over here. B on B goes to D. I have single B over here. Lastly, D on B. D on B is going to go to E. And since E is the final step, I say the input is going to be accepted by my deterministic finite automata. That confirms that the DFA is working, but it is very important that we check the vice versa example also to confirm whether it is rejecting the strings not ending in ABB too. So let's do that now. So consider an example like X A B A B. So it is not ending in ABB. Starting with X on A goes to B. I have BAB with me. B on B goes to D and I have AB with me. Then D on A goes to B. What is left with me is a single B, and now it is the time to decide the output. So if I check what is B on receiving small b, it is going to D, and since D is not the final state, I am going to say that this input will be rejected by my DFA. So here we complete with the problem, and that's the way to solve it. Regular expression to NFA, NFA to DFA, and DFA to minimize DFA. In the next session, we will take one more problem for practice before we go on to the next topic. Thank you.